All right, I have posted the solution of the exam 2 on the Blackboard, but here I will just make a very short video to very briefly explain some of the solutions of the two problems, the last two problems. And then the problem 4 is basically a flat plate with constant surface temperature of 90 degrees C, and the cold water is 25 C at a certain velocity. The dimensions are given 1.5 meter long and 0.5 meter wide. And the question asks us actually what is the heat transfer rate on the middle strip, which I have highlighted in the diagram from 0.5 to 1.0 meter. So this is a convection transfer. So what we need to do is we need to find out how the edge changes on the surface, right? So in order to determine the edge, the behavior, convection behavior within this range between 0.5 and 1, we need to find out the edge. And then, however, in order to find the edge, we use Nusselt number and then the Reynolds number. And we know the correlation between Nusselt number and the Reynolds number has two types. One is the laminar, and then the other one is the turbulent, right? So we need to find out what is on this strip. And in order to calculate the Reynolds number, then we need the property. Property includes the viscosity, density, the specific heat, maybe not specific heat, of conduction coefficient of the water, the fluids, and also the Prandtl number. And then in order to do that, we need a reference temperature. And for this flat plate, we already talked about it many times. So this is a flat plate. Either it's laminar or it is turbulent, whatever it is. The temperature that we are interested is for the fluids within this region, and we don't know the temperature. However, we know the temperature on the both sides of this blue region. So the upper bound and then the lower bound. And then the upper bound is the infinite temperature of the water, and then the bottom boundary layer, the bottom boundary of this blue region is the surface temperature. So the T reference temperature is the average of the infinite temperature and then the surface temperature. The infinite temperature is 25 C. And then the surface temperature is 90 C. Or here, same thing. Divide by 2. That actually gives us 52.5, right? No, 57 actually. 57.5 C, and which is about 330 K. And then you look for property of the 330 K. Some students somehow calculate this wrongly, and then this would be wrong. I will take a few points off unless your property will be totally off. And then some students use the air table instead of the water table. That will make everything changed, completely different. Then 330 C is right here. It is the water table. And then this is the specific volume. And it is the inverse of the density. So I also detail something here. So the specific volume of the fluid, specific volume is 1 over density. And then also the number that you see here, there's one student or two students. Actually, they didn't know, somehow they didn't know this number and this number are a number after you have some multiplication for that. So what we see here is 1.101 is what? You can look at the header of this column. the header of this column is this guy. So it is VF times 10 to the third. This is what this number is. So just do this, right? So this is what is number. And in other words, the specific volume of the fluid is actually this. And then therefore the density is 1 over the specific volume, right? And of course, I'm wrong here because I'm not using the 330. So 330 is this guy. 330, this guy. So if I use a 330 number, then this is not 1.001. It is 1.1. Oh, this is actually something. 1.016. And this is 016. And this gives you 980 something, 84-ish. And that's the density of the fluids. And if you want to have the unit, that's kilogram per cubic meter. As you can see, it is exactly the inverse of the units that you have here, which is meter cubic per kilogram. Yeah. All right. And then once you have the property from here, then you can calculate the Reynolds number. And then again, what we are interested in is in this section. And then first of all, we want to find out what is the flow on this section. So we need to find out the Reynolds number at beginning of the section we interested. And also we want to find out the Reynolds number at the end of the section. So after you put those in, density, infinite velocity, which is 0.3 meter per second, and then the x equals to 0.5, and then you have the viscosity. And then what you have is actually 3 10 to the 5. And then if you put x equals to 1, it is 6 to the 5. So in other words, the beginning, it is a laminar flow. At the end is a turbulent flow. And for those of you who don't know, the criteria is the critical Reynolds number criteria is 5 to the 10 to the 5. So at the beginning, it is less than 5 to the 5. It is laminar. At the end, it's 6. It's greater than 5 to the 5. So it is turbulent. So if you want to visualize that section, you can imagine let me do a better drawing. Okay, so if I have a plate like that, and then the first section and then the second section, the flow would actually coming from left side, it will be laminar, and we know at this point it is still laminar, and we know at this point it's already turbulent, right? So there is somewhere will be transition from the laminar to the turbulent, somewhere, we don't know. And then we need to calculate this point, which is a critical position XC here. And we know this is 0.5, and we know this is 1.0, and then the XC is somewhere in between. And you can calculate that. So the critical Reynolds number equals to the density, velocity, and then the position of the critical point over the viscosity. So you can calculate that is basic critical Reynolds number times the velocity or viscosity, and then the density, and then velocity. It is 0.8 meter. So this position now equals to this number. And now we know there are two regions on this section that we are interested. The first section is the laminar section, and the second section is the turbulent section. So we have to integrate the behavior of the two sections. So that's what my solution is doing. And here I want to point out some error or mistakes that students do. So if I have an extra slide, okay. So one approach that some students did is actually they use the middle point. So they were saying, okay, so if you want to calculate this section, then they will calculate the middle point here. Middle point. This is x equals to 0.75 because the left side is 0.5. The right side is 1.0. So the middle point is 0.75. Then they use this Reynolds number, and then this Nusselt number, and this convection coefficient. So they use the Reynolds number x equal to 75, Nusselt number 0.75, and then convection coefficient x equal to 75 to calculate calculate for the entire section for this. This can be done or cannot be done, really depending on how you understand it. So imagine you have a function as a function of x. So if this is the x, and then if this is the function of something, and then if this function is, let's say, a linear line, then what you can do is you can integrate this black curve, get the area under the black curve, right? That's the purple area. And you also can do an approximation if you know the middle point. So the middle point is somewhere here. So you, instead of doing integration, you can use this middle point as the average value to calculate this rectangle. This rectangle is close to what we had 1 second ago for the purple shape, right? So this is the rectangular, and what I draw in a minute ago was something like that. And these two cases are actually similar to each other, not too far away from each other. The reason why it is because the black curve is a monotonic function. It can be approximately as a line. So if you have a straight line, then the area under the curve like this will be exactly same as the square of the blue shape. This is because the function itself is a line. This is a line, linear line. But however, if your function cannot be approximated as a line, then you cannot do this. For example, if your function is something like that, which is our h as a function of x, and if our section is here, as you can see, your purple area under the curve is these curves, these area. And you cannot use a middle point to approximate as the average, because this case, your middle point is almost similar to the high end of your curve. And as you can imagine, if your function of the black line is also different, for example, if your black line is this way, you also have a transition. And now you can see your integral will be this purple area, but however, your middle point will be here, and your approximation will be this blue area, will be much smaller. So if you don't have a monotonic function, you cannot use a middle point as a approximation of the average value. Okay, so this is one mistake that students do. And of course, some students didn't even consider the integration or this average middle point at all. Some students just use the first point as a Nusselt number and then the convection coefficient to calculate the entire surface, which is wrong. Or some students use the last number, which is also wrong. And then some students use the middle number. Middle number is a bit better than the beginning and the end, but still it is also not correct because we have a transition here in this case. And then there's one more student who actually explained his thought. I also put a second type of solution on my solution as well. Second type of a method approach on my solution as well. So if you want to use the Nusselt number average from the table, for example, it is this, right? And the other one is actually equals to a very complicated one. So it is 0.03 something, Reynolds number 4, 5. And then this is the end for that. And then if you use this, you have to be very careful because these average numbers are a average. This average number as a function of x is a average from x initial equal to 0 to a position of x. So in order to use these two numbers, you have to calculate the heat for the entire first two sections, and then you calculate the heat for the first section alone. Then you subtract the first number by the second number. Subtract the second number from the first number. That's how you do it. Oh, okay. So if you still have questions to see why you are losing points, or if you have if you think I didn't understand the way that you do and the way you do is correct, you can explain to me separately. All right, so now let's look at the second problem, which is a single wire in air. And one thing is most of the students actually have question about the second one because the first one is a steady state problem. So what I'm gonna address is I want to address the same thing again and again. I really want to see the student know why they are using this equation or that equation. And then, however, I understand that if the student blindly use an equation, as long as the student is correct, then there's no way for me to see the student actually doesn't understand the problem, and then student only blindly copy a solution or copy the equation. But if your equation is wrong, then there's no way I'm gonna give you much points, especially if you copy a solution instead of the governing equation. So for any object, okay, for any object, what we always do is we use the first law of thermodynamics. What it says, the change of the thermal energy of the object equals to the energy this object automatically generated. Of course, in most of the cases, or in many cases, object doesn't really generate any energies. But however, for this one, it does. What it does is actually when you have a electrical heater, like that, And for those of you, I think space heater, I have a space heater in my office, but I cannot show you right now. But if you, okay, let me take a picture of my space heater. So for example, if you have a space heater before, something like that, right? So if you turn on this stuff, you'll see the wires in it will become red, and it will give heat. It will blow heat towards the space or towards the room or towards me, right? So the way it works is basically whenever a current passes through a metal wire, the electrical power will be converted. Electrical energy or electrical power will be converted to thermal energy, thermal power. And then this will become a so-called energy generation. That's the thermal energy of the object, the hot wire, the wire that becomes red. It is generated inside the hot wire. And this electrical energy equals to, electrical power equals to I, that's the current square times the resistance. And this resistance is electrical resistance. And then everything is given here. The electrical resistance is 0.2 ohm. Yeah. All right. And then if I construct the energy balance for this piece of wire, all right, this piece of wire, that's the object. The change of the energy of this object equals to the generation inside this object, and then plus the Q. If I define the Q in this direction, then it will be plus Q. If I define the Q in this direction, then it will be minus Q. I hope this already become obvious, because the way that I define right now, the Q is leading from the object, so therefore it's minus. The previous definition, it was the Q going into the object, so it is plus, whichever we define. And then sometimes you also have the work done towards the system. So if you have a compressor, then you will do it. But however, for most of the chemical engineering cases, this work will be ignored because most of the fluids are not compressible. So, so this will be the energy equation, which is thermodynamics first law. And then in this case, this would be this. And the Q that is being transferred into the object, as I defined with this arrow, that will be H times the surface area of the object times the infinite temperature minus the T, because this is because the way that I define the arrow. If the arrow is opposite, then these two temperatures will be swapped. All right. So now let's look at this equation again. So the equation says the change of the energy of this any object equals to the energy that is being generated inside the object plus the Q T infinite minus T, right? And then the generation energy, I change it into this. All right. So this is the equation that we describe the nature. That's what happens in the physics. I hope, okay, that's just my wishes. I hope if the students can understand this and know how to generate, how to write down these equations, how to write down the equation, describe any object that you see in your life, that would be the best. And then I will tell you the second best. The second best is the student don't know where the equation come from, but however, the students know exactly where the solution comes from and also know how to adjust, how to use the correct equation, correct solution, and also make adjustments, make more modifications based on the problem that you are dealing with. But this is the best if the student can describe what's going on in front of you, okay? And then let's look at this equation. For the first subproblem, most of the students, 99% of the students are all correct here. And this is similar to our first section of the semester. Most of students knows the generation of the heat has to be transferred to the ambient. So what they do is EG equals to so this is how much heat generated, and this is how much heat that's been transferred away to the ambient. So most of the students do this correctly, and they got the correct answer, which is 69 centigrade or 70 C. But if you know this equation correctly, if you write down this equation correctly, then for the first problem, it says steady state. The steady state means this guy equal to 0. So therefore, and then as you can see now, this is exactly what you have been doing. The heat generated must be equal to the right side of equation. You move this item to the right side and you flip the order of these two temperatures. As you can see, the heat generated has to be transferred away to the ambient. This is just the natural conclusion if you draw this equation correctly, okay? And now the second problem is the case, the left side is not 0 anymore for the B. So the change of the object thermal, so any object, okay? So I still draw an object. Any object, the thermal energy can change of this any object can be described as its temperature, and then how much material it has times the specific heat, and then times the temperature change. That's the change of the thermal energy. And then the left side is this, the right side is still the same. And then you can solve this equation. And of course, in this case, you have to use a Biot number to verify if you can use the lumped thermal capacitance approach. So actually, I learned this ALTC from students. I never thought about this, but the lumped thermal capacitance approach. And then the way that you calculate the Biot number is this. So the ratio between the conduction and the convection resistance. So what you do is the H is 40 from problem, and the L is the ratio between the volume and then the surface area. For cylindrical species, for cylindrical objects, the volume is the cross-sectional area. Cross-sectional area is pi divided by 4 divide the diameter square and then times the length. That's the volume. And then the area is the circumferences of a circle, which is pi d times the length of the cylinder. So you can see the pi cancel each other, diameter cancel once, and then the length is also cancel. So it's actually quarter of diameter. And then the numerator is K. K is the conduction coefficient of the object, which is given is 50. So you can put it here. And this actually is 0.0.8, is very, very small. So it is much less than 0.1. So ALTC is correct. Therefore, this equation is correct. And then once you have this equation, you just solve it. And then I realize many students actually don't know don't write this equation, but somehow they got the solution of this equation. So I cannot remember now. So they somehow have this something like this. And then there's something here. And then this is the initial temperature minus the infinite temperature. And then they also have the same thing here. And then the exponential of another something. I didn't recognize this solution, but there is one student who wrote down this solution and however got some wrong number. And it got to be something wrong there. But at that time, I didn't recognize this solution. So I may even put a question mark there. If you are that student, your equation is correct, you can come back to me to explain to me. Maybe I should deduct less points than what I deducted already. I tried to find back the exam, but I couldn't find it afterwards. So if you are that person, you can let me know. But later on, I realized this solution may be correct. So as long as the students use this solution correctly, then you should be able to get 1 or 2 points from me.